Imagine a planet adrift in the darkness of interstellar space, untethered to any star, silently moving through the galaxy. No sun warms its surface. No familiar night sky shines upon it. These are the rogue planets, orphaned worlds cast out from their home systems, roaming between stars for eons. While our telescopes have catalogued thousands of exoplanets orbiting distant suns, the vast population of starless wanderers remains largely invisible, hidden in the cold void. Rogue planets challenge our understanding of planetary formation and dynamics. How many exist? How did they get there? Could some harbor internal heat or even subsurface oceans? Could they carry the building blocks of life across the galaxy? These questions stretch human imagination, forcing us to consider planetary science on an unprecedented scale. The existence of rogue planets is no longer theoretical. Observations and surveys have confirmed a handful of these hidden travelers, and simulations suggest that they may outnumber the planets bound to stars. They are a testament to the chaotic, dynamic nature of planetary systems, and they hint at a vast, invisible population quietly traversing the galaxy. Rogue planets are often born in the same way as regular planets, within the swirling disks of gas and dust surrounding young stars. Gravity gathers material into planetesimals, which collide and merge to form fully fledged planets. But not all planets remain tethered to their star. Chaotic interactions, particularly with giant planets, can fling smaller worlds into interstellar space. Consider a young planetary system with a Jupiter-like giant. Its immense gravity can destabilize orbits, triggering close encounters that sling neighboring planets outward at incredible speeds. Over millions of years, multiple interactions may eject planets entirely, sending them adrift. Some may escape their star's gravitational pull with velocities of several kilometers per second, beginning lifetimes of wandering through the galaxy. Collisions also play a role. Violent impacts can fragment planets or disrupt orbital stability, producing multiple smaller rogue worlds. Others may form independently as failed stars in dense molecular clouds where insufficient mass prevents nuclear fusion. Regardless of origin, these objects share a common fate, untethered, solitary, and traveling through the cold darkness between stars. Understanding ejection mechanisms requires advanced simulations. Astronomers model gravitational dynamics, planetary interactions, and stellar evolution to predict the number of rogue planets and their likely properties. Results suggest a staggering number, possibly tens of billions in the Milky Way alone. Most remain invisible, but their presence has profound implications for planetary science, galactic evolution, and the potential distribution of life's building blocks. Detecting a planet with no host star is an extraordinary challenge. Unlike traditional exoplanets, which can be observed via their gravitational tug on a star or the dimming of starlight during transits, rogue planets emit little to no light. In the darkness of interstellar space, these worlds are effectively invisible. Astronomers rely on indirect methods. Gravitational microlensing is among the most powerful tools. When a rogue planet passes in front of a distant star, its gravity bends and magnifies the star's light, creating a temporary brightness spike detectable from Earth. Microlensing surveys have already revealed candidates, confirming that free-floating planets are real. Infrared telescopes provide another avenue. Rogue planets retain some heat from formation and radioactive decay. While faint, this residual warmth can emit in infrared wavelengths, allowing instruments like Spitzer or the Wide-Field Infrared Survey Explorer, WISE, to detect them. These observations suggest a surprising diversity of sizes, from Earth-sized planets to gas giants several times the mass of Jupiter. Rogue planets vary widely in size, composition, and internal structure. Some are likely terrestrial, rocky worlds similar to Earth or Mars. Others are gas giants, comparable to Jupiter or Saturn. Without the heat of a nearby star, their surfaces can be frozen solid, but internal heat can persist for billions of years, driven by radioactive decay or residual formation energy. Some theorists speculate that subsurface oceans could exist on larger rogue planets. Insulated beneath thick layers of ice, internal heat could prevent freezing, creating potential niches for life, even in the absence of sunlight. Such possibilities expand the definition of habitable environments and suggest that life may not be limited to planets orbiting stars. Magnetic fields may persist in some worlds, generated by molten cores or conductive layers. These fields could shield potential atmospheres or internal oceans from cosmic radiation. Some gas giants may retain thick hydrogen envelopes, trapping heat and prolonging internal energy. Observational constraints are limited, but modeling suggests a remarkable diversity in the thermal, structural, and chemical properties of these silent wanderers. Rogue planets are not rare anomalies. Simulations suggest they may outnumber the planets bound to stars in the Milky Way. Estimates vary, but some models indicate 1 to 2 rogue planets per star, implying tens of billions drifting through interstellar space. These hidden travelers represent a vast, largely invisible population shaping the dynamics of our galaxy. The distribution of rogue planets is influenced by stellar density and galactic evolution. Denser regions such as the galactic bulge may host higher concentrations due to frequent gravitational interactions and more chaotic early planetary systems. Conversely, the outer disk and halo may contain fewer, slower-moving wanderers. Over billions of years, rogue planets migrate, influenced by the galaxy's gravitational field, passing through star-forming regions, spiral arms, and even near stellar systems like our own. Microlensing surveys have confirmed some of these predictions. Observations toward the galactic bulge reveal transient brightening events consistent with free-floating planets. While only a fraction of the total population is observable, these detections hint at a vast population of invisible worlds, silently moving between the stars, shaping our understanding of galactic structure. Rogue planets may also influence the formation of other systems. Passing close to young stars, they could perturb protoplanetary disks, trigger planet formation, or even collide with existing bodies, creating fragments and debris. Their role as dynamic agents in the galaxy underscores the interconnectedness of planetary systems and highlights the importance of studying these orphaned worlds. One of the most provocative questions surrounding rogue planets is whether they could support life. Traditional habitability relies on proximity to a star, but rogue worlds challenge that notion. Internal heat sources, such as radioactive decay, tidal forces, or residual heat from formation, could maintain liquid water beneath thick ice layers. Consider a massive icy rogue planet with a subsurface ocean. Encased beneath kilometers of frozen water, insulated from the cold vacuum, life could theoretically exist in conditions analogous to subsurface oceans on moons like Europa or Enceladus. Without sunlight, ecosystems would rely on chemical energy, hydrothermal vents or radiolysis, breaking down water into usable molecules, providing the foundation for microbial life. Rogue planets could also act as vectors for panspermia, carrying organic compounds or even microbial life between systems. During close passes near star systems or collisions with other bodies, material could be exchanged. Over billions of years, the galaxy may be sprinkled with life-bearing material, making these wanderers potential couriers of biology. Moreover, the diversity of rogue worlds, ranging from small rocky planets to gas giants with hydrogen envelopes, suggests a wide range of possible habitats. Even in deep space, far from starlight, conditions might exist for chemical complexity, prebiotic chemistry, or extreme microbial life. The very existence of rogue planets expands our understanding of habitability, forcing us to reconsider life's potential distribution in the galaxy. Observing a planet without a host star is no small feat. While microlensing remains the primary method, infrared detection provides complementary information. Rogue planets retain heat from formation, which radiates in the infrared spectrum. Instruments like WISE and the James Webb Space Telescope can potentially detect these faint glows, revealing size, temperature, and even hints of atmospheric composition. Future surveys will improve detection rates. The Vera C. Rubin Observatory, with its wide-field, high-sensitivity imaging, promises to capture transient events caused by passing rogue planets. Advanced algorithms, including AI-driven pattern recognition, can identify microlensing events in real time, enabling rapid follow-up observations. Direct study of rogue planets is a far greater challenge. They move quickly relative to background stars, often without predictable trajectories. Missions would require fast, autonomous spacecraft capable of intercepting a moving target millions or billions of kilometers away. Concepts include laser-propelled microprobes or advanced ion drives, allowing spacecraft to reach rogue planets and study them directly. Even without interception, analysis of infrared emissions, gravitational effects, and microlensing data allows scientists to model their structure, composition, and potential habitability. Each observation expands our understanding of the galaxy's hidden travelers and provides clues about planetary system evolution, galactic dynamics, and the distribution of potential life-supporting environments beyond traditional exoplanets. Rogue planets do not drift entirely in isolation. As they traverse the galaxy, they occasionally encounter stellar systems, dense molecular clouds, or even other rogue worlds. These interactions, while rare, can have profound consequences for both the wanderer and the systems it passes near. A close approach to a star can gravitationally perturb the planet's trajectory, altering its velocity or potentially capturing it into orbit. Though such capture events are uncommon, they could explain some anomalous exoplanet orbits observed around distant stars. In young stellar nurseries, where stars and planetary systems are packed closely together, rogue planets may play a role in shaping emerging planetary systems through gravitational nudges or collisions with protoplanetary disks. Collisions between rogue planets and smaller interstellar objects may also occur. While catastrophic impacts are statistically rare due to the vast distances between objects, even a single event can release fragments, dust, or organic material into the galaxy. These fragments could serve as seeds for future planetary formation or, intriguingly, as vectors for prebiotic compounds. The possibility of interstellar encounters raises fascinating questions about galactic ecology. Rogue planets may be agents of dynamism, subtly influencing the architecture of star systems, redistributing matter, and participating in a vast invisible network of cosmic motion. Though hidden, their influence ripples across the galaxy, a testament to the complexity and interconnectedness of the Milky Way. While the probability of rogue planets colliding with a star or another planet is low, the consequences are dramatic. A high-speed impact with a star-bound planet could strip atmospheres, generate enormous heat, or scatter debris into space. In some cases, such collisions could trigger secondary planetary ejections, creating additional rogue planets and perpetuating the cycle of interstellar wanderers. Catastrophic events also shape our understanding of the galaxy's evolutionary history. For example, simulations suggest that early in the Milky Way's life, frequent stellar interactions and chaotic planetary systems may have produced a vast population of rogue planets. Many of today's hidden travelers may be remnants of these violent epochs, carrying the scars of collisions and the chemical signatures of long-destroyed planetary systems. Cosmic chaos also includes interactions with molecular clouds. As rogue planets pass through dense interstellar regions, they may experience drag, accrete gas, or collect dust particles on their surfaces. These subtle interactions could alter their chemistry, thermal properties, or even potentially trigger chemical reactions, further diversifying the properties of orphaned worlds. The study of these processes is still in its infancy, but models increasingly suggest that rogue planets are dynamic participants in galactic evolution. They are not merely passive travelers. They interact, collide, and influence the broader structure and chemical evolution of the Milky Way. The mysterious nature of rogue planets invites speculation. Could some rogue planets harbor atmospheres thick enough to support complex chemistry or even primitive life? Could internal oceans beneath icy shells maintain microbial ecosystems powered entirely by geothermal heat? Some theorists imagine rogue gas giants with massive hydrogen envelopes retaining heat for billions of years. These planets could support subsurface oceans on orbiting moons, creating isolated, sunless habitats. In a universe increasingly defined by extremes, rogue planets expand the boundaries of what is possible for planetary environments. Even more speculative scenarios explore technological implications. Could advanced civilizations detect or even traverse rogue planets to escape the constraints of their home systems? In a galaxy where interstellar distances are vast, a rogue planet might serve as a mobile outpost, carrying resources, energy, or habitats across light years of empty space. While these ideas remain in the realm of theory and imagination, they highlight the profound significance of rogue planets. They are not just scientific curiosities, they are windows into the diversity of planetary possibilities, challenging assumptions and inspiring new ways of thinking about the galaxy. Rogue planets present both opportunities and challenges for humanity. Detecting and studying them pushes the boundaries of technology, observation, and imagination. Future telescopes and surveys will uncover more of these objects, while AI and autonomous systems may allow for rapid identification and follow-up. One day, humanity may attempt to intercept or study a rogue planet directly. Missions could include flybys, orbiters, or even landers, powered by ion propulsion, nuclear engines, or laser-driven sails. Such missions would provide unprecedented insight into starless worlds, their internal structures, chemistry, and potential for life. Ethically, engagement requires care. Rogue planets are pristine, ancient objects, often untouched by stellar radiation or human activity. Exploration must balance curiosity with preservation, ensuring that scientific inquiry does not inadvertently destroy or contaminate these cosmic relics. The study of rogue planets also reframes our cosmic perspective. We are no longer limited to the immediate solar system. Humanity can reach outward, observing objects that have traveled across light years, shaping our understanding of galactic processes, planetary formation, and the potential for life in the darkest corners of space. Ultimately, rogue planets remind us that the galaxy is not empty. Even in the vast darkness between stars, life's building blocks, dynamic worlds, and cosmic messengers are constantly on the move. They challenge us to expand our thinking, our technology, and our imagination, inviting us to participate in the ongoing story of the Milky Way. The coming decades promise remarkable advances in the study of rogue planets. New telescopes, sensitive to faint infrared emissions, will detect smaller and colder wanderers than ever before. Surveys like the Vera C. Rubin Observatory and the James Webb Space Telescope will expand our catalogue of hidden travelers, while advanced AI will process vast amounts of data to spot subtle microlensing events in real time. Direct exploration remains a formidable challenge. Rogue planets travel quickly relative to background stars and have unpredictable paths, making interception missions technologically demanding. Concepts like laser-propelled microprobes or autonomous ion drive spacecraft could one day allow humanity to study these worlds up close. Even a flyby or remote sensing mission could reveal atmospheric composition, surface characteristics, or internal heat, offering unprecedented insight into planetary processes outside of starbound systems. Long-term ambitions may include orbiters or landers, capable of studying internal oceans beneath icy shells. These missions could confirm whether rogue planets are merely cold, lifeless wanderers or dynamic worlds with potential habitats. Every step forward in detection and exploration will deepen our understanding of the Milky Way, the diversity of planetary systems, and the potential distribution of life in the galaxy. Rogue planets are more than scientific objects. They are profound symbols of the galaxy's hidden complexity. Their existence forces humanity to confront immense scales of time, distance, and isolation. Each planet drifts through interstellar space for billions of years, independent of stars, witness to cosmic history far older than our civilization. These hidden travelers challenge the anthropocentric perspective. We are accustomed to considering planets in relation to stars as habitable zones or sources of energy. Rogue planets remind us that life, chemistry, and planetary processes can exist far from the familiar warmth of a sun. They expand our understanding of what a world can be and what it might harbor. Culturally, rogue planets inspire wonder and imagination. They appear in literature and art as symbols of solitude, resilience, and the unknown. In the scientific imagination, they are laboratories for studying extreme planetary conditions and testing hypotheses about habitability and galactic dynamics. Finally, rogue planets illuminate humanity's interstellar potential. Observing and eventually visiting these orphan worlds pushes the boundaries of exploration, technology, and philosophy. They encourage us to cultivate an interstellar mindset, humility in the face of cosmic scales, curiosity to understand the unknown, and responsibility to explore with care.